Okay, everybody, so far you've learned about graded potentials, you've learned about how an action potential fires, and you've learned what the graph looks like of an action potential. What we still need to take a closer look at is how action potentials propagate all the way down an axon. So I'm drawing the beginning of an axon with this representing our axon hillock, and I will refer to that as segment 1. And then here we have segment 2. This is just a way to better visualize what happens when an action potential propagates. So I'm just artificially creating these segments, kind of like we did when we learned about graded potentials. And please assume that we have our voltage gated channels in these segments. So these are the voltage gated channels. Let's not forget that we also always have leakage channels. Let's just represent those as follows. And let's not forget too that there are always some sodium-potassium pumps present, and I'm going to just indicate them with stars like that. So those are our sodium-potassium pumps. And I'll just draw one here and there. Clearly these pumps are responsible for restoring concentration gradients, while the leakage channels are present all throughout the membrane. And I'm only focusing on one side of the membrane. You guys, you need to assume the same thing is happening here. Notice too, very important to point out, that we're going to be first studying propagation of the action potential along an unmyelinated nerve fiber, or propagation of action potential along an unmyelinated axon. That's what I meant to say. We will, after we've learned how it all works in an unmyelinated axon, then take a look at how it happens in a myelinated axon. Okay, so if we continue to use our light blue to indicate the arrival of graded potentials, and they summate, they reach -55, you know that whole story by now, and that triggers the opening of our sodium channels such that sodium rushes in and we see that this first segment now is starting to depolarize. So here we go, while the remainder remains at rest, etc. Things are going to get a little complicated, so be ready. As our sodium voltage gated channels open, you know that that is represented by the ascending limb of our action potential. As all of the sodium is beginning to rush into our cell membrane, into the cell membrane of the axon, that sodium is quickly going to start trading places with negatively charged ions in the next segment in both directions. On both sides of the membrane, we see that ions are trading places. This should remind you very much of how a graded potential migrates. And that is exactly what's happening. We're going to see that a local current once again migrates. So while our action potential is occurring, the inward current that is formed by the influx of sodium is going to lead to a local longitudinal current parallel to the cell membrane, such that the next segments that border the first segment slowly but surely start to become depolarized. Now, it's not of much importance to us that this segment over here gets depolarized, because there are no voltage-gated ion channels. We are interested in how much this segment that I have circled with, that I have labeled segment 2, how well this one is depolarized. And what happens is that enough ions trade places to where this next segment becomes depolarized strong enough to where it reaches threshold. And of course that means that these voltage gated channels will open up. I'm getting a little bit ahead of myself because this is not going to happen unless this action potential has completely finished and has made it all the way to its resting membrane potential. So while this action potential is occurring in the first segment, the local current migrates into the next segment, and this occurs in both directions. We're not interested in this previous segment because there aren't any voltage gated ion channels. The local current will be able to maintain pretty good strength because this segment is just right next door and there are voltage gated ion channels here, such that these ion channels will now open up. So the moment our action potential has finished in the first segment, it will recreate itself in the next segment. So you now need to assume that the first action potential that I'm showing here in the first segment is not there anymore. It has recreated itself. This is the same action potential but recreated. And then we're going to see once again that as this action potential is recreating itself in the second segment, the ions are going to trade places on the inside of the cell membrane and on the outside of the cell membrane. Once again, ions move in both directions, and we're going to see that our action potential will yet again recreate itself in segment 3. Why isn't it going to recreate itself in segment 1? That all has to do with the fact that this whole action potential must start, peak, and completely repolarize before it can recreate itself. It's because of this very reason, because there's a beginning and an end to this action potential, that we cannot see our action potential propagating backwards. So the propagation is always going to be away from the action potential area. Let me turn that off, I'm sorry. Okay, so we call this propagation, and this will continue all the way till we reach the axonal terminals. Now you may ask, why can this action potential maintain its strength despite the fact that there are all these leakage channels? Well, it is actually quite challenging. The fact that all of the voltage gated channels are situated very close to one another, and again we need to assume these are both sodium and potassium voltage gated ion channels, we're going to see that these action potentials are recreating so close to one another that the local current manages to maintain its strength pretty well. Is there always the threat that there is so much leakage that perhaps by the time we reach the fourth segment that the action potential can't recreate itself? There is that possibility, yes. But let's assume that that isn't happening, and let's assume that the action potential manages to reach the axonal terminals. Now, how does this all work in a myelinated axon? Well, that's what we're going to take a look at next.